Okay, and some more. So there's only just a tiny bit more revision here. And pretty much everything you need should be here really. Okay, so partial derivatives of this function of x and y with respect to x and y. So the partial derivative of z with respect to x. So what you're going to do is differentiate it with respect to x, treating y as a constant. So this is what partial differentiation is. Think about climbing up the mountain. The north-south coordinate changes, but the east-west does not. So here it's like the x is changing, but the y is a constant. We're not specifying what it is, but it is a constant. We'll differentiate term by term, fixing constants. So derivative of x squared with respect to x is 2x. Now we've got x multiplied by y to the power of 5. When we differentiate with respect to x, y is constant, it's fixed, and so y to the power of 5 is also constant. Now what's the derivative of x with respect to x? 1. Then on the next one, fix the constant. Now you got minus. It's like multiplied by minus 1. 6 is a constant, and with respect to x, y is a constant. And then the derivative of x cubed with respect to x is 3x squared. Plus, now if y is a constant, so is y to the power of 4, so the derivative of y to the 4 is equal to 0. And we can tidy that up if we want. It's, say, 2x plus y to the 5 times 1 is y to the 5, minus 6 by 3 is 18, and then you can do yx squared or x squared y, and of course they're numbers, so the order doesn't matter. Okay, and similarly we can differentiate partially with respect to y, and this means you're traveling, say in that picture with the mountain, you're traveling due east or due west. You're not changing your north-south coordinates, so in this one the x is kept constant. So this is, when we're differentiating with respect to y, this is just a constant. The derivative of a constant is 0. Plus, so with respect to y, x is a constant. So we fix the constant x, and the derivative of y to the power of 5 with respect to y is 5y to the 4. Then we fix the constant here, minus 6x cubed, and the derivative of y with respect to y is 1. And then finally, the derivative of y to the 4 with respect to y is 4y cubed. So this is actually revision. This is x multiplied by 5 multiplied by y to the 4. Order of multiplication of numbers doesn't matter. If I want, I can write it as 5x times y to the 4. Minus 6x cubed times 1 is minus 6x cubed plus 4y cubed. Okay. It's going on about notations there, but it's not too important. There's some exercises here just to get you going a bit, and the solutions are down there if you're stuck. Okay, so why did we look at this? Because I want to look at differentials and differential error analysis, and in particular we're going to focus in this module on rounding error. So I got, using the fact that many of the function y fx that we see in engineering are analytic, that means they have Taylor series, this gives us a way of approximating the change in the calculation of a function, right? So we got an idea, we've got a function which we're thinking about here as a formula. Not every function is a formula, but here they are. And we're thinking it's just something that depends on one number. So you calculate one number and use that number for a calculation. So for example, the area of a square, you measure the side length and use that measurement to make a calculation. And the question is, how does the change in the measurement, this is what you would have done last year, measurement error, cause an error in the calculation? Now we're going to work with eventually the errors or rounding errors. So we write the Taylor series. So f of x is equal to f of a. Now f of a, as we're going to see down below, a is our measurement. We'll probably see that at some point. Plus the derivative of the function evaluated a times x minus a. So this is using stuff. And then after that, it's plus terms of order x minus a squared. So they're all multiples of x minus a squared. So they're x minus a squared, x minus a cubed, which is x minus a multiplied by x minus a squared, etc. And we can use the equals because this order actually means loads of terms. So this just means that the terms beyond this point are powers of this or greater. That's another way of looking at it. So what we're saying here is this still technical? No, it's going to be something like measure x is equal to a when x is in fact equal to a plus delta x. So the idea here, so if we kind of give an idea here. So for example, so suppose this is the measurement and this is the true value. So we'll give kind of an idea of that. So suppose you measure something to be 1 point, let's say 8, 1, 2, 3, 4, 0, 1, 1, 2, 9, dot. Sorry, that wouldn't be the measurement. So that's the true value. So you measure this to be, say, 1.81. Yeah. That's your measurement, and the true value is something like this. So then what you're going to have is that the true value, I have to be careful here because it's going to get a bit messy. Yeah, so the true value is equal to the measurement, 1.81, plus the error in the measurement. And in this case, the error is the difference between the true value and your measurement. So i.e. 1.81 plus 0.00234, dot. Okay, so this is the idea. You measure, this is the true value, this is your measurement, but there's an error in the measurement. The difference between the true value and what you measure it to be. And the question is, like if you're to calculate, say if this is an area, the area of a square, you should be using this number, but you use this number. And the question is, how does that error in measurement mess up your calculation of the area? That's what this is about, okay? And so we're kind of doing that down here. So what we're doing here is we're saying, okay, x equal to a plus delta x. So this is the measurement. This is the true value. And so we have that x minus a, which occurs up here, is actually the error. It's the difference between the true value and the approximation. So what we have is f of x is equal to f of a plus this stuff here. F dash of a times delta x plus, and remember x minus a is delta x, so this is delta x squared. And the idea is we're saying that delta x should be small, relatively small, and so if you take, in particular, you're probably thinking of it as less than 1. And so if you take squares of it, or indeed higher powers, it's going to be even smaller. So for example, suppose we're talking about an error of 0.1. If you talk about 0.1 squared, it's 1 over 100, it's even smaller. So all these things, if the error is small, powers of the error are going to be small. So what we do is we just kind of throw out this bit. Now that makes this an approximation. So let's just write that down underneath. So f of x is approximately f of a plus f dash of a times delta x. So that's using the assumption that this thing is quite small. So this equals is no longer there, but there's a small difference, hopefully a small difference between them. So in what we get now is that f of x, so if x is the true value, f of x is throwing the true value into the thing you're calculating. That's the true thing that you're trying to calculate. Now a is what you measure, and you put it into the formula. This is what you calculate. So the true value, what you're trying to calculate, what you actually calculate, and then this would be, if you do the calculated bit plus this error, you get the true value. So this is an estimate then of the error in your calculation caused by the error in measurement. So this is kind of covered a bit what we're talking about already. So what we get is the true value of something, some calculation, is the calculated value that you get using the measurement, and then this is the error. So you can approximate the error like this. So you get error in the calculation is approximately the derivative evaluated the measurement times the measurement error, and we use a symbol like this, so derivative times error. Now this is a formula, and this is an idea that I think can be made intuitive, and in a normal year I would spend probably a bit more time explaining this, but because, and then what I do is I don't put this kind of a formula on the exam paper, but because there's no, all the assessment is open book, I won't actually spend that time today. Okay, so what we're going to focus on is where the errors come from. Now we'll have measurement errors, but mostly we're going to be interested in rounding errors. So what is the effect of, instead of using say 1/3, we use 0.33. And what will be the approximate effect on our measurements? So in this section we see the effect of rounding error on your calculation. The lesson I want you to learn here is to keep as many decimal places, and even not even decimal places, but significant figures in your intermediate calculation. So when you're making a calculation, it can be like quite a long calculation, don't, in as much as possible, don't round until the very end, until you're presenting your answer. Because if you round in the middle of a calculation, numbers you use in a calculation are like measurements, and so if they have rounding errors, you're putting them into more formulas, and those errors can get worse and worse and worse. Now the truth of the matter is, it probably won't be a big deal in your engineering career, particularly with factors of ignorance/safety. So multiplying by 1.5 will usually be larger than any rounding error. But I still think it's an important thing to understand that 1/3 is, for example, is not equal to 0.33. And saying that 1/3, for example, as some people sometimes do, or say 2/3, say for example, is equal to 0.6, that is bad. Now if you do 2/3 is equal to 0.6667, it's probably not the end of the world, the buildings won't fall down. But the difference between 0.6 and 2/3 is quite big. And like even if you look at say 5/3 and 1.6, imagine if you did this to the power of 5. So let's look at 5/3 to the power of 5. Take away 1.6 to the power of 5. Now if these were equal, this would be a very, very small number. It's not a small number. And in fact, like rounding errors in mortgage calculations can cost tens of thousands of euros. It's kind of my hobby horse. So this is why I include this section. It's nice for you because it's revision of something that you actually did last year. So what we saw in Maths 60/40, we should have seen, I have no idea what. Oh, I think what we saw was, oh yeah. So if you have a function of two variables, you can do similar analysis to before, and you get that the error in the measurement of f is approximately given by df max, which is equal to the derivative of the function with respect to x that's evaluated at the measurement times the error in the measurement of x plus the derivative with respect to y times the error in the measurement of y. And you need these absolute values, but that would have been covered in Maths 60/40. I might say a little bit of down below. There's a further remark that you can look at here if you want, that kind of like, why is this a sum? Well, this kind of argues why it should be a sum. So a similar principle, that's the same, I would say. I mean, you're not using the true value. Say if you're using 1/3, if instead of 1/3 you use, say, 0.3. Now, why is the calculator given this? Some people don't seem to notice this. Press it again, it's loads of trees going on forever and ever. So if you use 0.33 instead of 1/3, there's it's a measurement error, essentially. So think of rounding errors as errors in measurement. How do they affect or cause errors in calculation? Suppose we have a formula for a property P relate to other properties A and B by, so we just got some formula here, say P, A and B. Suppose you have values of A0 and B0, they're your measurements of A and B, but you round them. So say instead of using pi, use 3.14. Instead of using 1/3, use 0.33. So what you can do is you can keep track of the errors in this calculation due to these rounding errors, and the maximum absolute value gives an estimate of this. So the error in the calculation of P caused by these rounding errors is approximately the maximum absolute value of the differential, which will be equal to dP dA evaluated at the measurement times the rounding error in A plus dP dB evaluated at the measurement times the rounding error in B. The reason we use absolute values is because we don't want rounding errors to cancel each other out. We want to allow for the worst case scenario. Okay, now there's probably just one small thing that's come into my head there. It's really not that important, but like say if you do work with 5/3, uh, like look at some possible approximations. So 1.6 is bad because it's actually not. Like what is this equal to? It's equal to 1.6666. It goes on forever and ever. 1.6 is a bad approximation to this. 1.7 is a little bit better, but in general, two significant figures, in my opinion, isn't a lot. My understanding is in engineering, use three significant figures, which would be 1.66, but there's a more accurate one than 1.66, which would be 1.67. Because if you round this, you get 1.1, 2, 3, and the 6 rounds this off. This isn't too bad. If it's me personally, I would use a minimum of 4 significant figures. But of course, I wouldn't do that. I'd just use 5/3. Okay. Now, the other thing I want to see is an understanding about what we're doing here. So, and about how this is rough. So this so we've got some numbers that we're using, a mixture of numbers and measurements, and we're banging them into a formula. Now, we're maybe rounding numbers, so they're errors, and maybe in our measurements have errors as well. And the question is, how do those errors in measurement and rounding cause errors in calculation? It's approximately this. This is quite rough. This is only really good to one significant figure. Okay, and that's written down here. So our job will be to, in general, unless it asks for something different, present your calculation as what you think it is plus or minus an error. Now this is something you can do in your projects. You can do this error analysis. I hope your lecture last year told you this, that when you produce a measurement in engineering, you can give, here's what you think it is plus or minus an error. And that's a good thing to do. Recommend rounding the rounding error to one significant figure and then match the decimals. Like for example, is there any point writing down 1.23 as your measurement plus or minus 0.3? Well, there's no real point in including the 3. Why? How could you be so precise when the error is like 0.3? So what you should do is, if this is what you calculated, this is what you estimate to be the error, you should match the precision. So get this to one significant figure, and then say how many decimal places 1, and then get this to one decimal as well. So you're better off saying 1.2 plus or minus 0.3. Look how big the error is, 0.3. There's no point talking about the 3. Like, it would be weird if you didn't know, like if you only knew your bank balance. Think of it this way. So someone asks you, how sure are you about your bank balance? And you said, oh, I only know it, I think to the nearest 20 euros. And they say, well, what do you think your bank balance is? You wouldn't, or maybe I'll say nearest, 20 euros. You wouldn't say 71 euros. That makes no sense. You just say 70 if you only know it to the nearest 20. Now you could argue, maybe say 75, but we won't worry about that either. Okay, as engineers, all measurements should also come with units and therefore the errors. Okay, there will be marks deducted in this question for missing units or incorrect rounding precision. Yeah. Okay, let's do some examples. And let's say we'll get one example and we'll all be done. Yeah. If a loaded beam has a bending moment measured in kilonewton meters given by this, estimate the error in the calculation of the bending moment if we round to one decimal place at x equal to 1 meters and the location of the maximum bending moment. Okay, so we can calculate that m of 1 is equal to this and m of 2.4 is approximately equal to this. Now, the idea here is that if we're rounding to one decimal place, this is like our measurement, while this is the true value. Okay. Now the 1 is a little bit weird because, so like if you measure it to be 1, you know, really what does the 1 represent? It's everything, isn't it, between 0.95 and 1.05. Now I'm going to put a square bracket, this is being overly fussy, the square bracket here, and these are meters, square bracket here because 0.95 to rounds up to 1, and a rounding bracket here because 1.05 actually rounds up to 1.1. So the rounding bracket means it's everything up to 1.05, not including 1.05. Okay. So you can sub in the 1 into this, and you wouldn't sub in this value, you'd sub in 2.4 is the idea, if you're rounding to one decimal place. Now this should explain that if you're rounding to one decimal place, then the error is 0.05. If you're rounding to 2 decimal places, the error will be 0.005. So see here, everything between these two numbers rounds to 1, and the biggest difference between the true value and this measurement, this approximation, is 0.05. So the biggest difference between what you're using 1 and the true value is 0.05. So 1 decimal place gives this error. So now here we've only got a function of a single variable, so we don't have to have two terms, we've only one because it just depends on one thing. So we're going to write down that the rounding error the error in the calculation of the bending moment caused by the rounding error is approximately dm max. Okay, and it'll be equal to differentiate. Now I can put in these partial ones, but there's really no need because it only depends on x times the error in x. Okay, and what we're going to do now is differentiate this thing. So the derivative of m with respect to x is equal to fixed constant differentiate, fix to 1/5, and the derivative of x cubed is 3x squared, minus fix to 9, what's the derivative of x squared? 2x, plus fix to 40, what is the derivative of x? 1. And we're interested in this, so this is always calculated at the measurement. So the measurement as such here is 1. So we bang in x equal to 1 into this, we should get 1/5 by 3 by 1 squared. There, we'll just throw it in here. 1/5 by 3 by 1 squared minus 9. Well, maybe we say 9 by 2 is 18 by 1 plus 40. I'm just substituting x equal to 1 into this. What do I get? I should have left more space here. Anyway, 1/5 by 3, 1 squared is just itself, minus 18 plus 40. So this comes out as 22.6. And therefore the error in the calculation of the bending moment at 1 meter is approximately this derivative, which is 22.6, times the error, which is 0.05. This is equal to, so it's derivative times rounding error. The absolute values means that if you got something negative here, you make it positive. Because when you talk about, you're going to include plus minus anyway. So just take everything positive and do plus minus. What do we get here? 1.13, and we said this is rough. So round this to one significant figure, which is 1. And then match the precision. So this is no decimal places, or it's the nearest 1. So put the calculation to 1 decimal place. The nearest 1 is 31. So you get that the bending moment at 1 is 31 plus or minus 1 kilonewton meters. So rounding the distance to 1 decimal place, to the nearest 10 centimeters, can cause an error in your calculation of the bending moment of up to 1 kilonewton, which is about 3% here. Okay. So now let's do another question. Or sorry, not the other question, the other bit. Now, what we have here is again, so we have this, however, at the maximum, this is something we would have seen previously, I think, the derivative with respect to x is going to actually be 0. Now, what we're going to do is we're not going to sub in the exact value because we're rounding this to 1 decimal place. We're going to put in 2.4, but I expect that to be small as well. So let's see. So delta m, so this is at the maximum bending moment. If you round the position x to 1 decimal place, what do we get? So this will be approximately, right, what's the derivative here? It's this number here, say 3/5 x squared, we're going to put in 2.4 there, minus 18 by 2.4 plus 40 times the error. Now, if we're rounding to one decimal place, it's 0.05. Now, you could actually go away and calculate it exactly. Well, we won't say that. 2.4, 2.4. I think if you put in the thing with the square root, well, you shouldn't, because you're calculating these at the measurement, equals to, bang this into the calculator, and we get 3/5 by 2.4 squared minus 18 by 2.4 plus 40 multiplied by 0.05. Look at this small number we're getting. 0.0128, which is approximately 0.01 kilonewton meters. And so we round this to the same precision, the nearest two decimal places, 46.92. So you can see that at the maximum, the rounding, the error is tiny. And this is something we would have seen earlier. And it's kind of a situation where a lot of the things that are problematic in terms of rounding, so for example, something like this, is something you're not necessarily going to be worried about. Like, you're not really worried about the bending moment at 1. You're more interested in the maximum bending moment. And lots of things in engineering that you look at, rounding just isn't a problem. So for example, here, it just doesn't really matter. And the reason is that the derivative is really, really small. That means the rate of change of the bending moment is really, really small with respect to x. So if you change slightly the x value from the true position of the maximum to a rounded effort, you're not getting much of an error. Okay, so we've only one more example, which we'll do in the next lecture.